Great models don't happen by accident. They're the result of fast experimentation, smart resource use, and efficient training workflows. In this section, you'll discover how Azure Machine Learning helps you train models faster and more effectively, from scaling compute resources to streaming the way experiments run. As your models and data sets grow, optimizing training becomes critical. You'll explore techniques that let you run experiments in parallel, accelerate iterations, and refine models with less friction. So you spend less time waiting for training jobs and more time improving model performance and delivering real impact. Now let's move from exploratory notebooks to production-ready scripts. Notebooks are ideal for interactive experimentation, debugging, and quick iterations. From production training jobs, needing code that is clean, repeatable, and automated. Converting a notebook to a script typically involves 3 steps: removing non-essential or exploratory code, refactoring logic into reusable functions, and testing the script from the terminal to ensure it runs reliably as a command or pipeline job in Azure ML. For step-by-step guidance, see the URL at the bottom of this slide. And consider this use case. After prototyping a classification model in a notebook, a data scientist must convert the code into a training script that Azure ML can run repeatedly on compute clusters as part of an automated experiment here in CI/CD workflows. Best practice is to keep notebooks for exploration, but maintain a separate cleaned training script structured with functions and clean inputs and outputs that makes experiments reproducible, simplifies job scheduling, and ensures the code scales smoothly from experimentation to production workloads. When you're ready to run a training script in Azure Machine Learning at scale, you package it as a command job, a repeatable, trackable unit of execution that runs in your workspace with the right code, dependencies, and compute. Here we see a breakdown of the configuration into the essentials: experiment name, which groups related runs; job display name, which is a human-friendly label for this run; code, which is the folder containing your script; and the command here is the exact file entry point to execute. The environment will package the runtime and it's needed on the compute, and compute will run the job. To configure a command job with Python SDK version 2, you'll use the command function. To run a script, you'll need to specify values for the following parameters: code, command, environment, compute, display name, experiment name, and then together these settings make your run portable across machines and reproducible across iterations. A best practice here is to keep your command parameterized, where we have input arguments, output to a known folder, and then pin it to your environment, and use consistent experiment name plus descriptive display name so runs stay organized and able to be audited. When you want to reuse the same training script with different inputs, you turn it into a parameterized command line program. And Azure ML command jobs are built for exactly that. Here we see the standard pattern: input arg parse. We want to define your inputs with the argument parser, including the name, the type, and the default. Then pass values at runtime so each job run is intentional and comparable. A simple example is a training with a different dataset path and regularization rate, like the code shown here. This is the key to bridge from it works in my notebook to it runs reliably anywhere. The command is the same when testing the Python script in a terminal or when you're running the script as a command job. So the exact invocation you validate locally is the one you submit to Azure ML. No rewrites, just a different execution environment. Consider that you're tuning a diabetes classifier and want to sweep reg rate across values where keeping the script identical is needed. You run the same command with different arguments to generate multiple comparable runs. Best practice here is to keep parameters explicit and well-typed, set sensible defaults, and log parameter values, for example with MLflow, so every run is reproducible and easy to compare later. Now it's time for our knowledge check. Question 1. A data scientist wants to run a script as a command job to train a PyTorch model, setting the batch size and learning rate hyperparameters to a specified value each time the job runs. What should be done by the data scientist? Answer: add arguments for batch size and learning rate to the script and set them in the command property of the command job. Question 2. A data scientist has trained a model in a notebook. The model should be retrained every week on new data. What should the data scientist do to make the code production ready? Answer: convert the code to multiple functions in a script that read the data and train the model. You've now seen how efficient training turns good ideas into scalable production-ready solutions by moving from notebooks to scripts, parameterizing your code, and running repeatable command jobs in Azure Machine Learning. You unlock faster iteration, better resource utilization, and cleaner experimentation at scale. This is where machine learning shifts from explore and test to run with purpose with the same code. Validating locally, now executes reliably across clusters and experiments with full traceability. With these foundations in place, you're ready to go even further, accelerating experimentation through parallelism, automation, and advanced optimization techniques that lets teams iterate faster, train smarter, and continuously improve model performance in real-world ML pipelines. Great models don't just work once, they keep improving as new data arrives. In real-world scenarios, you often move from experimentation to automated training scripts, retraining models regularly, and measuring whether those updates actually make the model better. For instance, a diabetes prediction model might be retrained each month as new clinical data is collected. With MLflow integrated directly into the Azure Machine Learning, every training run automatically captures parameters, metrics, and artifacts so you can clearly see how performance changes over time. In this module, we'll explore how to run training scripts as Azure ML jobs with MLflow tracking, and then dive into the run results, reviewing metrics, parameters, artifacts, and saved models to evaluate progress. Here we see the steps to track training runs with MLflow. When executing scripts as Azure Machine Learning jobs, the process is straightforward. Submit your command job, which is automatically associated with an experiment, train the model, and then review the log parameters, metrics, and artifacts to compare runs and evaluate performance. Tracking parameters, metrics, and artifacts works similar in notebooks and scripts. One of the differences between notebooks and scripts is when working with notebooks, you need to create an experiment manually. When running a script as a job, an experiment is automatically created. MLflow provides two flexible options for logging. You can enable automatic tracking with MLflow Autolog, or you can explicitly log values and files using the MLflow.log functions. For example, if you run a diabetes prediction training script as a scheduled Azure ML job, MLflow can log metrics like AUC or accuracy for every run and store artifacts such as the trained model or the evaluation plots. This makes it easy to compare results directly in the experiment history and determine whether new data or parameter changes improve performance. Best practice here is to enable auto-logging for quick, consistent capture of standard metrics and supplement it with targeted custom logs for domain-specific signals that you want to monitor closely across runs. Ready to turn experimentation into repeatable, optimized training? In this exercise, you'll run a model end-to-end in Azure Machine Learning and learn how to capture the evidence behind every run, first with custom logging for the exact metrics and artifacts you care about, and then with auto-logging for fast, consistent tracking with minimal code. By the end, you'll know how to train smarter, compare runs faster, and make model improvements with confidence, no guesswork. Please use the URL here below for our lab instructions. Now it's time for our knowledge check. Question 1. A data scientist trains a regression model and wants to track the model's performance by storing the root mean squared error with the experiment run. Which method can be used to log the RMSE? Answer: the MLflow log metric. Question 2. When a data scientist enables MLflow autologging, where can all model assets be found? Answer: in the model folder under Outputs and Logs. In this section, we move beyond experimentation into production-ready machine learning workflows. You learned how to transform exploratory notebooks into streamlined Python scripts, run those scripts as Azure Machine Learning command jobs, and use MLflow to track every training run, capture parameters, metrics, and artifacts, so model performance can be compared with confidence. Together, these practices create a repeatable, scalable workflow where training is automated, results are transparent, and improving models becomes a data-driven process rather than guesswork. Once you have a model that runs, the next challenge is making it perform even better, and that's where hyperparameter tuning comes in. In this section, we'll learn how Azure Machine Learning helps you systematically explore combinations of training settings to uncover the configuration that delivers the strongest result. Instead of guessing which parameters might improve performance, you'll use Azure ML tools to efficiently search, evaluate, and compare multiple model variations, turning experimentation into a structured, data-driven process that helps you find the best performing model faster. Hyperparameter tuning addresses this by training multiple models using the same algorithm and training data, but different hyperparameter combinations, then evaluating each run using a target performance metric, such as accuracy or AUC, to identify the best configuration. In Azure Machine Learning, this process is streamlined through sweep jobs. A sweep job runs a trial for each hyperparameter combination, executing the training script repeatedly with different parameterized values and logging the resulting performance metric in every run. For example, if you're training a diabetes prediction model, a sweep job could test learning rates like 0.01, 0.1, and 1.0 to determine which configuration produces the most accurate predictions. Best practice here is to define a clear optimization metric and a focused search space for hyperparameters. This keeps experimentation efficient while helping you systematically discover the configuration that delivers the best model performance. Here we see the end-to-end workflow for hyperparameter tuning with a sweep job in Azure Machine Learning. Create a training script for hyperparameter tuning similar to any training script, but with two key additions: an argument for each hyperparameter you want to vary, and an MLflow logging for the target performance metric, so Azure ML can evaluate every trial. Configure and run a sweep job next by defining a base command job that points to the training script and specifies the parameter space. The sweep job then automatically launches multiple trials, each training the model with a different hyperparameter combination. For example, when tuning a diabetes prediction model, the script might run several trials with different learning rates and regularization values, with MLflow logging accuracy, or AUC, so the system can identify the best performing configuration. Once the sweep begins, monitor and review the child trials inside your Azure Machine Learning Studio. Each trial logs metrics and artifacts, and you can visualize and compare runs, adjusting charts to examine relationships between hyperparameter values and results. Best practice here is to start with a clean, parameterized training script and a clear optimization metric, for example, maybe maximum AUC. Then analyze trial visualizations in the studio to quickly see which hyperparameter values consistently improve performance before promoting a model to the next stage. A search space is the set of hyperparameter values your sweep job is allowed to try, and defining it well is what turns tuning from guesswork into a disciplined, high-signal experiment. Listed here are two hyperparameter types: discrete, which is a finite set of values, and continuous, which is any value along a range. Discrete hyperparameters are ideal for options like batch size or a fixed list of regularization values, and you can define them with choice values like 10, 20, and 30, choice value ranges like 1, 10, or choice values equals maybe 30, 50, 100. For example, you can also sample discrete values from distributions such as Q uniform, Q log uniform, Q normal, and Q log normal, which quantize values into steps of size Q, useful when you want rounded valid increments. Continuous hyperparameters like learning rate can be sampled from uniform, log uniform, normal, or log normal to explore real valued ranges efficiently, often with log distributions being especially effective for rates that vary by orders of magnitude. Best practice here is to keep the search space tight and realistic. Use choice for parameters with known safe values. Use log uniform and log normal for scale-sensitive parameters like learning rate, and avoid overly wide ranges that waste trials on obviously bad configurations. Here we see how Azure Machine Learning decides which hyperparameter combinations to test while running a sweep job. The selection depends on sampling method you configure. With grid sampling, every possible combination of discrete hyperparameters in that defined search space will be evaluated. This is ideal when the number of combinations is small and you want exhaustive coverage. Random sampling instead selects values randomly from the search space and works with both discrete and continuous hyperparameters. Note here that SOBAL is a variation of random sampling. It adds a seed so experiments are reproducible and distributes sampled values more evenly across the search space. Bayesian sampling, on the other hand, uses Bayesian optimization to choose new hyperparameter combinations based on performance of earlier trials, focusing on search on areas likely to improve results. It only works with choice, uniform, and Q uniform parameter expressions and can't be combined with an early termination policy. For example, when tuning a diabetes prediction model, random or Sobol sampling might explore combinations of learning rates and batch sizes across the entire space, while Bayesian sampling quickly zeroes in on the combination that yields the best AUC after the first few trials. Early termination policy is a key technique for making hyperparameter tuning more efficient. When you run a sweep job in Azure Machine Learning, you might define a maximum number of trials, but a smarter approach is to stop runs early when you're clearly not improving model performance. That's exactly what an early termination policy does. It monitors intermediate metrics from each trial and halts runs that are unlikely to outperform the best models so far. Continuous hyperparameters present an unlimited number of possible values to choose from. You'll most likely want to use an early termination policy when working with continuous hyperparameters and a random or Bayesian sample method. This combination allows the system to explore the search space broadly while quickly eliminating poor-performing configurations. For example, imagine tuning the learning rate of a fraud detection or diabetes prediction model, where the parameter can take many continuous values. As the sweep job runs, trials with configurations that produce weak early accuracy or high loss can be stopped before they finish training, freeing computer resources for better candidates. Next, let's see how to configure an early termination policy in a hyperparameter sweep job so Azure Machine Learning can stop weak trials early and conserve compute resources. Two key parameters control when and how evaluation occurs. Evaluation interval, which defines how often the policy checks model performance each time the primary metric is logged, and delay evaluation, which postpones enforcement, so the first few trials or iterations can run before the policy begins judging the results. There are three decision strategies. A bandit policy drops trials that fall outside of a specified slack range of the current best model. A median stopping policy, which halts runs that perform worse than the median or completed trials, and a truncation selection policy, which removes the lowest performing percentage of runs. For example, when tuning hyperparameters for a diabetes risk model, a sweep job might evaluate accuracy every epoch evaluation interval, but wait a few iterations, and then run the delay evaluation before applying the stopping rule. Poorly performing trials can then be stopped automatically once they fall behind the pack. So a best practice here is to combine early termination with well-defined performance metrics using an approach like the bandit or the median policy, so weak configurations are pruned quickly, allowing compute resources to focus on the hyperparameter combinations that are most likely to produce a high-performing model. The bandit early termination policy, which helps a sweep job drop weak trials early so compute resources focus on the configurations most likely to succeed. In Azure Machine Learning, a bandit policy stops a trial if its performance falls below the best model so far by a defined margin. For example, the code here applies a bandit policy for a delay of 5 trials, evaluates the policy at every interval, and allows an absolute slack amount of 0.2. Imagine the primary metric of model accuracy. If after the first 5 trials, the best model scores a 0.9, then any subsequent model must achieve at least a 0.7, which would be a 0.9 minus 0.2 to continue. If a trial exceeds 0.7, it keeps running. If it drops below that threshold, the system terminates the run early. You can also apply a bandit policy using a slack factor, which compares the model's performance as a ratio instead of an absolute margin. Consider when tuning a classification model, early trials might reveal that only a subset of hyperparameter combinations achieve acceptable accuracy. The bandit policy quickly halts the weaker trials, so compute is redirected to better candidates. The median stopping policy is an early termination strategy that prevents wasted compute by stopping trials that perform worse than the median of a previous run. In Azure Machine Learning, you can configure it with parameters such as delay evaluation, which postpones evaluation until several trials have completed, and evaluation interval, which determines how often the policy checks performance. For example, the following code applies a median stop policy with a delay of 5 trials and evaluates the policy at every interval. If the primary metric is accuracy, and after 5 trials, the median accuracy is 0.82, a new 6th trial must exceed 0.82 to continue. Otherwise, the policy stops the run early and to avoid wasting resources. Consider while tuning a diabetes prediction or a churn model, Azure ML may run many hyperparameter trials, but the median policy quickly eliminates configurations that underperform relative to the pack. So a best practice here is to use a median stop policy when exploring large search spaces. It ensures underperforming runs are halted while still giving promising trials enough time to show meaningful improvements in the target metric. The truncation selection policy speeds up hyperparameter tuning by eliminating the lowest performing trials at each evaluation interval. For example, the following code applies a truncation selection policy with a delay of 4 trials. It also evaluates the policy at every interval and uses a truncation percentage of 20%. During a sweep job, the policy periodically examines the log metric for all running trials and removes the worst performing portion, defined by the truncation percentage. So compute resources shift towards stronger model candidates. Consider a quick scenario where accuracy is the primary metric. When the accuracy is logged for the 5th trial, the metric should not be worse than 20% of the trials so far. With only 5 trials, 20% equals 1 trial. So if the 5th run has the lowest accuracy of all the runs, it's terminated. If its accuracy is better than the weakest trial, then the run continues. Best practice here is to use a truncation policy when running many trials in a large search space. Pruning the bottom fraction of runs early helps your sweep job focus compute on the most promising hyperparameter combinations and reach an optimal model faster. In this demo, we're going to tune hyperparameters using a sweep job in Azure Machine Learning, which is how you move from a good model to the best model. Instead of manually guessing values, a sweep job systematically explores different configurations in parallel and identifies the optimal combination based on your chosen metric. You'll see how this process builds directly on tracked experiments in MLflow and produces repeatable, scalable results. This is a core optimization technique in MLOps and a key skill tested in AI-300 for building high-performing, production-ready models. So hello everyone, and welcome. In this demo. We're going to take a simple machine learning model and make it smarter, not by changing the data, not by rewriting the algorithm, but by tuning the hyperparameters that control how the model learns. And we'll do this using one of our Azure Machine Learning's most powerful features. That's a sweep job. So training a machine learning model is easy. Training a good machine model isn't. The difference is almost always coming down to what's called hyperparameters. So every machine learning model has hyperparameter settings that influence the training and things like the regularization strength, the learning rate, the batch size. These choices can dramatically change your model's accuracy, training time, and stability. And the truth is, picking them manually is slow and consistent and often just guesswork. So what we're going to do is we're going to move into how to use hyperparameter and sweeping job together. And what I'm going to do is right here, now in our Azure Machine Learning Studio, you will see I have a job running, and there it's right now. And what I'm going to do is I'm going to go down to notebooks, and we've seen these before in previous demos. And the one right here is to tune hyperparameters with a sweeping job. And so I'm going to pick this up off the file, and then we're going to use our sweep job here. So what we're going to do is we're going to see the choices that we can make right now. It's pretty dramatic, and you're going to be able to come up with a bunch of different ways of working with this as we move forward. We'll see that. So the sweep jobs are going to eliminate that guesswork for us. And they're going to let the Azure ML automatically try multiple hyperparameter combinations and run them in parallel. And then we'll be able to track the results, and it will be able to tell us which one performs the best. And so with this file, our notebook here, we're going to go get it from GitHub. And what we're going to do is we're going to give it a little bit of information here. Now, I already started running it because it does take a while to run. So I launched these simply by clicking here and then run this cell and all below, and that's what I did. And what we can see in this first cell, which is typically what we add here with, is the Azure ML package. If it's not installed, well, we're going to need to do that. And then we can scroll down and we can connect to the workspace. We're going to make sure that our Azure ML SDK is installed here also, and that's part of what is running right now. And if all our ducks are aligned in a row here, and what we can see is that we've set it up with our credential 2, and we can see a lot of that from this spot here. And then the workspace that we're going to use here, we're going to get into it right now, and what we can see is our training script down here. And so what we can talk about hyperparameters and these values that control how a model learns and what it learns from. It's not just learning from the data. In this notebook, we can see that the hyperparameter that we're going to be tuning is the regularization rate. And that's where we're going to focus on the logistic regression model. So what we'll see with this is that we have maybe to do too much regularization, so we are overfitting. And if we do too little regularization, then we are underfitting. And so it's kind of a trade-off here between fitting the training data closely and then generalizing well for the new one. And that's what we're going to try to focus on here. And so the right value is almost never obvious, which is why tuning matters. And so in this script, we will scroll down and you're going to see a little bit more of it here. So what's going on? It's kind of beginning here, creating a training script. As I scroll down, I can see, we're going to see the folder that script file goes into. And then down here, it's fairly lengthy script. And you can see some of the things we're going to have it do. And we're going to have it go in and read data, split data, train data, evaluate data. And as I go up here to the top, I can see some of the things that we're importing to really give us the ability to do the train test. Split the rock curves, the scores. We might want to add this. And then we can also see we're adding these, some of our libraries here. So what you can see here first is we have data that we're going to be training. And this lets us pass in a registered data set. So we're going to work with this, and we're going to move forward from here. And it's not hard-coded path here for the file. And we're going to see, what we're going to see is that we have a little bit lower down. There's an option here for the reg rate. So that's a little further down. This is kind of the key option here. This is our hyperparameter that will tune. And it's a little further down. Let me see if I can find it. Yeah, so down here we have our reg rate. And you can see the default is 0.01. So we have that, and we can see that there. And so that's helpful. And what we'll also note here is that when we talk about Azure ML, it doesn't tune models, it tunes arguments in our script. And what we're going to do is we're going to take a little look a little higher in our script. And what we're going to do is we're going to go see what it says. And I think the sweep job just finished, which is good. So we have something to look at, and we're going to come back in here, and you can see it's reading the data split. So the reading of the data here, then it's going to pull in the diabetes data set. Then eventually what it's going to do here is what we can see the split. It's going to split the data that's going to separate training and test sets, and that we can measure real performance with it. And then the training model is going to use logistic regression. Ultimately, what we'll see is we're going to pass in the regularization rates dynamically. And then we have also some log metrics, and that's a little bit lower down. And I'll kind of show that section here too. So there is our log metrics here, and you can see it off the MLflow log metric right there. And you can see too that we're going to be working with accuracy and AUC. And those are going to be there. And this is mandatory for a sweep job. And then we're going to create some log artifacts that we can find a little bit lower here. And you can see some of the things that we're making down here. So we have the rock curve image, it's captured. And so each run is fully reproducible. And then the sweep is ready also. So there's another script. There's a script then that's a little bit lower here. We can read a little bit of that information. Let me see that line. It's a little bit lower here in our syntax. So here we have it already. And we're going to try to go through the script that's sweep ready here. It accepts hyperparameters as arguments, log metrics consistently, and produces artifacts for comparison. That's ultimately what we're having it do. And so as I scroll down a little bit further, we're going to see our section on configure and run the command job here. So before we can tune anything, we need to do something very important. We run the script once as a command job. So the sweep jobs multiply whatever we've given them. If the script is broken, a sweep job breaks it 10 times faster, and it's more expensively. This job here is going to prove that the script ran successfully, and it proves data access works. I'm going to prove too that our metrics in the MLflow logging work in the environment is correct. And so what you can kind of see is we look through a little bit more of our command jobs here, some of the things that they do. Some of it's configuring a job, submitting the job, and it's going to do some of the testing, force the command job. And then you'll see that this has created a job for us to monitor. And so we can monitor the job. We'll see that in a bit. And also, as you scroll down here a little bit more, and in this section where we can define the search space. So as we look here, once we trust the script, we can define what values we want to explore. And also we can see here we have the choice values equal, and you can see it equaling three things: the 0.01, the 0.1, the 1. And what it's really telling Azure ML is to train one model for each of these regularization rates. We also are declaring our intent to not have, hard coding experiments going forward. So the idea here is that today we have it with 3 values. Tomorrow we could have it with 100 values to test for us. So this is an important option. And then as we scroll a little bit further down, you can see configure and submit the sweep job. And the sweep job here is our Azure ML. It's a way of it running many training jobs automatically for us, each with a different hyperparameter. So this looks like a good option here too. And as you look, we can see that it is the sampling grid. Here is setting sampling algorithm equals grid. is set to try every value in each search space. So we have that option turned on. Here we can see the primary metric that is essentially here. This metric must exist in our MLflow log, otherwise the sweep fails. So that's an important option. Goal equals maximize. This is our Azure ML automatically deciding which run is the best. And then we can use this to tell it which modules to run. And pardon me, we can tell it to run modules in parallel. And this gives us the fastest result here with our maximum concurrent trials of 2. So faster results, better compute usage. So what I want to emphasize here is that we didn't write these 3 training scripts. We just wrote 1, and now we let Azure ML do all the orchestration for us. So there's a lot of benefits of these sweep jobs, and we'll talk about these sweep jobs. What happens is that when we have them, they can run fast, they run in parallel, and it's consistent where we have the same data, same code, and it gives us a metric-driven selection. It's reproducible, so every run is tracked. It's scalable. Right now, you're having to do this manually, but when we have this, we could run 3,000 jobs if we wanted to, as an example. So by the end of the sweep job, we've removed all the guesswork from our model training. We've explored multiple configurations in parallel, and we have them logged and compared so that we can see them up against each other. And then we will take this to help us identify the best performing model within our job here. And we can see also that this is done with minimal effort. So this is really the power of Azure Machine Learning, automated scalable experimentation that helps you build better models faster with more confidence. This is how real teams tune models, is they use sweep jobs in hyperparameters here without having to rewrite code. So as we go down to the bottom here, we can see we have a little bit more of monitoring here is available. And as you can see, which one of the winning hyperparameters, and we want to be able to confidently use this in production with future jobs. So what we're going to do is we're going to go down to jobs and we're going to take a look there. And we do have this diabetes job running. That was one. And I'm going to click on that. And what we'll see is you get a lot of information about it momentarily here. It will take, let me click it one more time. And we'll get a little further into it. And then we're going to see the parameter space. You can also see that it used the grid as we told it. And it's a little bit more, it's telling us what it's done here. And one of the things we wanted to know, which was one of the best, was the maroon ticket, which is the best one, which if I scroll down a little bit, you can see a little bit more about the data used. It didn't fail, it completed the runs here. And we can see, and this one is our best trial so far. And I'm going to click on it actually, and I'm going to save this one for just a moment. And I'm going to go to the trials first, and you'll find you should be able to see the different runs in there. It gives you some of the metrics to look at and a little bit more. As you can see down below, you can see each one, maroon 1. Notice that you can look at the options here. So this is one of the best ones. I forgot the extension on this, but if you can see, actually it's the same as number 1, so that's the parent. And then we have different display options there that we can go back and look through. Scroll up again here a little bit. It shows you the hyperparameters involved. So that this training accuracy, lets you look at AUC, and you can look at that. It also gives you a lot of information there, parallel coordinate charts. We can change that out, and so it looks like, okay, so it's another automated job there that we can look at, and then running this, we can see it in 3D. I'm interested in seeing that option. But we can click one a little later, okay, and then we can go into metrics, and then in metrics we can see a little bit more here. Maybe it's still kind of creating everything for us, so I have to give it a little bit more time. Let me go back to the overview for a moment, and then we'll go back and take a look at, and we can see which one's the best one. The best one is the one right here, and we can see that it completed. We can find out a little bit more of the hyperparameter that it used, the model type that it worked with, the parameter down here, the regularization rate, and then you can see what it gave us here, metric-wise. And so I can get a little bit more information from this, and I can see the environment and go into the metrics, and it should highlight those metrics for us. So there we are. Any child jobs on this? No, not at this point. And some of this you may give us a little bit more detail. We do have a little bit of that output log there we can take a look at, so we can see a little bit of that went through. You can see some of the code there. And we'll see some Python available through here. Okay, so you get the idea. This is hopefully going to give you what you're looking for, which is, a lot less pain here when you're trying to decide what model to use. So the big takeaway is very simple. Hyperparameter tuning isn't magic, it's automation. And by writing parameterized scripts, validating them with command jobs, and scaling them with your sweep job, Azure ML turns your trial and error into a disciplined, traceable process. So this is where experimentation becomes production-ready machine learning. Command jobs prove your script works. Sweep jobs prove which version works best. So I hope you enjoyed this. See you in the next one. Now it's time to put your hyper tuning into action. In this exercise, you'll move beyond theory and run a real sweep job in Azure Machine Learning to systematically test different model configurations by creating a command job, configuring it as the base for the sweep, and submitting it for execution. You'll see how Azure ML can automatically explore multiple hyperparameter combinations to help surface the best performing model faster than manual experimentation. Please see the URL below for complete instructions on how to use the lab. Now it's time for the knowledge check. Question 1. You plan to use hyperparameter tuning to find optimal discrete values for a set of hyperparameters. You want to try every possible combination of a set of specified discrete values. What kind of sampling should you use? Answer: grid sampling. Question 2. You're using hyperparameter tuning to train an optimal model based on target metrics named AUC. What should you do in your training script? Answer: use a MLflow log metric statement to log the AUC. In this section, you learned how to systematically optimize model performance with hyperparameter tuning in Azure Machine Learning. You explored how to define a search space, choose an effective sampling strategy, and run a sweep job that automatically tests many model configurations in parallel. By structuring experiments this way, rather than guessing values, you can quickly surface stronger models and make tuning a repeatable, data-driven process that delivers better results with less manual effort. In this learning path, you explored how to operationalize machine learning and generative AI solutions with Azure Machine Learning, taking projects from raw data to production-ready workflows. You looked at how to design data ingestion strategies, experiment with and tune models, and track experiments with MLflow, while also converting notebooks to scripts and running scalable command jobs and sweep jobs to optimize performance. Just as important, you saw how to apply responsible AI practices and built-in Azure ML tooling to monitor, evaluate, and trust the models you deploy. Together, these capabilities turn experimentation into reliable, repeatable ML and AI operations at scale. This is the end of our first learning path, with so much more to come. Looking forward to seeing you in the next video. Thank you for joining us for this session. To continue your learning, watch other videos in this course, or explore more on Microsoft Learn at aka.ms/learn.